I will speak about my joint work with my colleagues from Ghent University about global pseudo-differential operators on the Lie group, cube minus 1, 1. Okay, here is the content of my presentation. Well, it's rather big, but I will drop some topics, just showing you what is done in this work. I will speak about a little bit about Lie groups, definition and properties, and then about convolutions on the Lie groups, and about pseudo-differential operators on Lie groups. We prove here all classical properties of classical pseudo-differential operators on Rn, for example, or manifolds. We repeat all the theorems and prove in our case. Then we define function spaces and some boundedness properties of operators, of pseudo-differential operators, such as Pfefferman theorem, Calderon-Weiland-Cook theorem, and some non-classical multiplier theorems, if I will have enough time. Then about spectral properties, such as Gochberg lemma and Atiyah-Singer feathers of index theorem. Okay, let me start. The open set, well, the cube minus 1, 1 in power n, it's a cube in Rn. We can enter it with the group operation x plus y divided 1 plus x multiplied by y. I mean the scalar product, of course. And it maps this G into itself, and it becomes group, Lie group, because it is also manifold, of course. It is a Lie group, very simple Lie group. And so we can have here, and we identified here the hard measure representation of this group. And of course, then we have the Fourier transform on this group. And that enables us to define the Hermander class of pseudo-differential operators on this group. And by quantization for a certain class of symbols, of course, which satisfy Hermander-like inequalities, with quantization, we define the pseudo-differential operator, which is in 0-1 formula, with the help of the Fourier transform, Fg and Fg minus 1. And then we analyze with the properties, boundedness and the composition, and so such different properties of this. What we prove? Asymptotic expansion of the composition, adjoint and parametrices. For the Hermander classes. Then mapping properties of these Hermander classes, well, as I told you, Calderon-Weiland-Cook and Pfefferman type theorems, and also boundedness of convolution operators with piecewise continuous symbols, in which sense we understand piecewise continuous on this cube. I will tell you later. And we also prove Gochberg's lemma on the compactness of such operators, and at conclusion, I will show you the Atiyah-Singer Fedosov index formula for these operators, for the Shubin's classes of symbols. Okay. The Fourier transformation and the convolution of functions on the interval minus 1, 1 in one-dimensional case was defined by Petrov using the diffeomorphism. He just defined it as an image of this diffeomorphism of the axis to the interval minus 1, 1. And he called it P transform, and it is Fourier, but he never realized, don't realize that it is the Lie group. It can be defined independently of the interval minus 1, 1. as a Lie group, if you identify the Haar measure and representation of this group and the Fourier transform. But he made a very important applications of this definition. He solved Prandtl, its integral differential equation of Prandtl, differential equation of Tricomi, and Lavrentiev besides integral equations, and also boundary value problems for Laplace-Beltrami equation on the sphere, and some other equations of mathematical physics. And his colleagues continues to apply this technique for different problems of mathematical physics. But as I told you, this can be defined independently as a harmonic analysis on Lie group -1,1. And we use this advantage to define independently Fourier transform and all this technique, and this enabled to define Bessel potential spaces, prove theorems on multipliers for convolution operators, and derive more precise results for the above-mentioned integral equations. I mean, solvability properties, a priori smoothness, and such things, if we have the full scale of such spaces. But it is the work which I am not going to speak about it here. After this work, I was guest in Ghent, and with my colleagues, we tried to apply this technique for definition of pseudo-differential equations on this Lie group, and derive the results for the pseudo-differential operators. And I will speak about these results. Well, Lie groups, definition and properties. Let me give you, for those who is not very much, how to say, familiar with this Lie group technique. Let me explain you some topics in this area. First of all, the group is, of course, it's a binary operation which maps any pair of this group to an element of the group, and it has the standard properties. This mapping has standard properties as the sum and the product. First of all, there exists a neutral element. It can be identity or it can be zero, which does not change the element. If you multiply by identity, the element remains the same, or if you add zero, it remains the same. Each element has inverse, its group, of course, and every element has inverse element. And the third is the associative. This operation is associative. Lie group can be commutative or non-commutative, but we will consider the group which we consider is commutative group. First fundamental fact, that on such groups, there exists an unique and invariant Haar measure, which enables definition of the integral, left invariant measure and right invariant measure. It's written here, what does it mean? In our case, left and right invariant measures coincide. So we have integral, we have definition, we have measure on this group, and it's unique, this measure. Second fundamental fact, there exists Fourier transformation, which has inverse and which is based on the Haar measure and the representation of this group. And the Fourier transform maps functions on the functions of the dual group, which is the representation, of course, dual group. I will explain this on the example. A third fundamental fact can be defined the convolution of functions on the Lie group. It's written here, the convolution. And this convolution can be written as the convolution operator. So you can take, oh, here is missing f minus 1, sorry. You take the Fourier transform of function, and then you take the multiply by function, by symbol, which is, well, okay. Well, it's everything is correct. Here is the simple property that the Fourier transform transforms convolution to the multiplication. And the convolutions, which is written here, K, operator K, by the Fourier transform can be written as a convolution operator with the symbol. Convolution means you take the Fourier transform, multiply by symbol, take inverse Fourier transform, and the convolution operator. And this is called this K is called the symbol of this operator. So on the group we have convolution operators, and the pseudo-differential operator is nothing but the same. Just the symbol depends on external variable. Euclidean space is a group, you know, and I will not dwell on this case. Euclidean space is a group, and the classical Fourier transform is the Fourier transform, and the Lebesgue measure is the Haar measure there, and the convolution is defined here by the formula y1, 1, 1, and the classical results, and the symbol here governs the invertibility or unique solvability of the corresponding equation. The symbol is important in this issue. Another example of the group convolutions on the groups and Fourier transforms is the half-axis. Here, the measure is dx divided by x. The Fourier transform in this case coincides with the Mellin transform, and the convolution is the integral equations with ratio of arguments. And again, the symbol here, which is the Mellin transform of the kernel, governs the solvability of this equation. And now the most important example for us, that's the group minus 1 in power n. Well, let me remind you here again what is the group operation here. Group operation brings x and y to x plus y divided 1 plus x scalar product with y. And this maps group to itself, and it is really a group, Lie group, and the measure, Haar measure here is x divided by 1 minus x xg squared. So it means that this space, for example, does not contain constants. The function should have some zeros at the endpoints to belong to these spaces, corresponding spaces. The invariance of this measure means that if you take the product of x with y and y is fixed, then you will get the measure dx again. That we have left and right invariance of this measure. Characters are this mapping. X is mapped to 1 minus x, 1 plus x, IC, and this maps the group to the Euclidean space. So the dual space coincides with the Euclidean space, Rn, and this mapping has properties that the product group operation over x and y is brought by this characters, by this mapping to the product of the characters in the character space. Okay, the Fourier transformation is here defined by the formula 2-1. Unusual form of Fourier transform, but this is Fourier transform on the group. And it has the inverse. The inverse Fourier transform is defined here. So we have Fourier transform, we have Haar measure, and now we have to define some spaces. Schwarz space, the classical Schwarz space, you know, it is the functions, consists of functions which have these seminorms, finite seminorms written here, and the similar Schwarz space for the group on the group, which we consider here, is the following. Logarithm 1 minus x module square in power n, and derivatives taken here are not simple derivatives, but they are so-called Fuchs derivatives, weighted derivatives. They are written here. And these derivatives, you see, if you take derivative, you have to multiply by 1 minus x squared. And this is the, natural derivative in this space, because by the Fourier transform, such derivatives are sent to the multiplication by the independent variable. It's written here. As it happens in usual classical Rn space with the classical Fourier transform. The differential operators, partial differential operators are sent there to the multiplication by the natural variable. And here is the same, but here the differential operator is this one, weighted differential operator. Okay. Well, then the dual space and so on, and we have now the global, I think the time is running very fast, and I have to accelerate a bit. Well, global Hermander classes. It is defined as usual, but the derivatives here by x is taken with these weighted derivatives. In this sense, everything is the same, but the derivatives are different, and it satisfies this inequality. And the quantization formula, which brings correspondence between the symbol and the operator. Quantization is here the same, as I told you, as convolution operator. You take Fourier transform of the function, it's missing here, so multiplied by the symbol, and take inverse Fourier transform. Here is missing, of course, the function, but you understand. And by psi here also with the missing again the brackets. This class of these operators is denoted by psi with these indices. It's a Hermander's class of operators, so for the M and rho delta type as a classical differential, pseudo differential operators. Okay, and the example of simple representative is a convolution operator, here written convolution, with differential operator. So convolution differential operator, it's a simple example of such pseudo differential operators. And the symbol is written here down. And it governs again the invertibility and Fredholm properties. Composition formula. The classical composition formula is repeated here, and it's written how this question and the asymptotic expansion is given with the help of this weighted differential operator. The adjoint differential operator is pseudo-differential, is again pseudo-differential operator, and with asymptotic expansion. Parametrics. If the symbol is elliptic of order m, it's written here 1, 3, 4. Then we can construct parametrics. Parametrics is constructed again by the standard formula with the help of these weighted derivatives. And all these results repeat the results from the classical theory. Function spaces. Function spaces that, well, we define LP space as the weighted space with this Haar measure. We take the convolution operator with this symbol here, 1 plus, here should be plus c squared for 1. With this Laplace, this is, Bessel potentials. Take these Bessel potentials and define in a standard way the Bessel potential spaces. which coincide with the similar spaces, but the derivatives are weighted derivatives again. We can prove theorems of multipliers. I dropped these theorems of multipliers. Well, for example, the functions of bounded variation, in certain sense of bounded variation, I gained again the multipliers here. Pfefferman theorem has complete analog here, as well as Calderon-Vaillancourt theorem for L2 spaces is also has the analog here, and the Gordon inequality we have here also, and Pfefferman-Fong inequality, and the Gochberg lemma. Gochberg lemma states that if the essential norm of the pseudo-differential operator is estimated from below by the supremum of the symbol, it is complete analog of the classical pseudo-differential for the classical, which was proved for the classical pseudo-differential operators. We get it here as well for our operators. And Atiyah-Singer, Fedosov theorem. Atiyah-Singer, here we have to restrict our class a little bit more and introduce the Shubin class of order 0. If we have the Shubin class of order 0, it's defined here by 5.2, then we have the Atiyah-Singer Fedosov formula. Atiyah-Singer proved it in a general case. Fedosov proved it for the case where for this simplified case, but much more transparent formula, which is written here. And here we have this connected with the winding number of the matrix symbol. For the matrix operator and matrix symbol, we have this Pfefferman for this formula, the full analog of the classical pseudo-differential, which was proved for the classical pseudo-differential equations. Yes, related papers. My paper about convolution equations on this Lie group is probably not published, but it is in ArcSym. Its references here. And I mentioned Petrov's paper and Suslina Petrov's paper also. The references are here. They, as I told you, they considered these integral equations and defined this Fourier transform for the interval and applied them to the problems of mathematical physics. Thank you for the attention.
Next question. Eu busquei sobre essa moto do Попробуйте вот сюда.
Is it clear that your group G is isomorphic to Rn?
Yes, of course. The isomorphism is very simple, and it was used, as I told you, by Petrov to define this Fourier transform.
Okay.
It's fully isomorphic, of course. The isomorphism is with logarithm and with exponential function. Very simple isomorphism.
So can we derive the harmonic analysis on G from the harmonic analysis on Rn?
Pardon? Harmonic analysis? Yes, of course. Of course, that is what was done by Petrov also. The harmonic analysis can be transformed from axis R or Rn also to the harmonic analysis on the group, on this group.
Okay.
Sure.
And what about the pseudo-differential operators on Rn?
Pseudo-differential operators on Rn. It also, they are isomorphic to pseudo-differential operators on group. If you apply this, yes, it's some kind of duality.
Thank you.
More questions, please.
Dear Professor, it seems to me that for your transform, it should be valid the Greenwich theorem that every classical differential operator is the singular integral operator. Is it possible to generalize the Greenwich theorem to your case?
Generalize what? Sorry.
A Greenwich theorem that each classical one-dimensional differential operator is singular integral differential operator.
Well, I cannot completely catch what you asked me. But if you mean the singular theory of singular integral operators,
Yes. Yes.
on the axis, of course, it is convolution operator. It's convolution operator, and it is, of course, can be singular integral operator on the axis -1, on the interval -1, 1.
Yes.
In this case, looks a bit different. But if you transform it to the axis, you will get the Hilbert transform.
Of course. Obviously, it is different. Obviously.
Yes, it looks different because the convolution here is different.
Yes, I know it, but it seems that it looks so similar that it should be valid. There's some variant of this Agronovich theorem.
Yes. Many things can be proved with the help of this, of course.
Thank you.
Yes.
Thank you.
Yes.
More questions, please? Then let me ask. Suppose that x times y is equal to -1. How do you define the group operation in this case?
X minus y is equal to what?
To -1. X times y is equal to -1.
Oh, no. -1 don't belongs to this group.
Sorry.
No, it's open interval.
X.
It's non-compact. It's actually non-compact manifold. And the -1 and 1 does not belong to this group.
Suppose that x is equal to -0.8 minus 0.6. Does this belong? And y is the same.
Well, what we say? Well, it is, at least, I understand what you asked me. This operation, x plus y divided by 1 plus xy, if x and y are between -1 and 1, this is also between -1 and 1. It is easy to prove. But not -1 and 1. It's excluded.
Сейчас, минус 0,8 на минус 0,8, минус 64, так? Минус 0,6 на минус 0,6, это минус 0,36. В сумме это минус единица?
Сейчас. Еще раз повторите цифры.
Минус 0,8, минус 0,6. Один вектор. И второй такой же. Минус 0,8, минус 0,6. Оба лежат от минус единицы до плюс единицы. Скалярное произведение ровно минус единица.
Не, подождите. Минус 0,8 и минус 0,6. Это, у вас два вектора, да? Один и тот же. 0,8.
А у вас сколько?
Да, понятно. Нет, можно и 1, можно 2, и можно n. Так, 0,8.
А где норма ограничения?
Нету ограничений. Главное, чтобы все элементы были между минус 1, 1. Хорошо, посмотрим. 0,8, 0,6 умножим на 0,8. Сейчас. Но оно должно быть внутри. Оно должно быть оба. 0,8 умножается на 0,8. Это 0,64, да? 0,64. 0,6 умножается на 0,6. Так, это тоже 0,36. Ну, это будет, внизу будет 2, а не 0. Потому что это положительное все. Так что делится на 2. И будет между нулем и единицей. Нет, ну не ищите здесь подвоха, потому что здесь подвоха нету, это точно совершенно.
Это не настоящий формалистский проект, там где 3 единицы минус квадрат совершенно. Это настоящий формалистский проект.
Если внизу у вас одинаковые x умноженное на y, if it have same, you have the norm of x square down stairs.
But not
And
about the
so,
norm given in the definition.
pardon?
Ой, хорошо, 1 минус, 1 плюс. Они все равно лежат в этом кубе.
1 минус, 1 плюс. Ну ладно, тогда наверху будет 0.
Хорошо. А 0 на 0 что? 0 на 0 определено, что ли, в данном случае?
А в данном случае определено это 0.
Окей, thank you. Yes, but, Володя, лучше подойди к микрофону, что там будет слышно. Ну, он можно к тому же.
Скажите, вот в одномерном случае там было очень много приложений. Вот конкретные уравнения, которые решались, да, вот этим преобразованием.
Да.
А в многомерном случае есть что-нибудь?
В многомерном случае, вот, например, Лаплас с фильтрами на сфере.
Это все равно одномерный случай.
Ну, почему одномерный? Лаплас с фильтрами на сфере – это двумерный случай все же. Ну, это там интегральное уравнение двумерное.
Не, я сам это делал, вы тут на меня ссылаетесь. Это одномерное преобразование все равно. А вот вы сейчас предложили многомерный
понятно.
случай.
Одномерная, но она с параметром, конечно. Одномерная с параметром. Ну, многомерные, ну, такие известные уравнения, как Лаплас, Бельтрам и так далее, в смысле Лаврентьева, Бицадзе, я не знаю таких примеров. Будет хорошо, конечно, если будут такие примеры интегральных уравнений.
Мне интересно найти ядра, которые вот соответствуют этому вашему примеру.
Можно взять, знаете как, прямо взять прямое произведение, допустим, Лаврентьева, Бицадзе на приколе. И получите вот такие двумерные уравнения. Вот для чего это пригодно, я не знаю.
Понятно. Хорошо, спасибо.
Пожалуйста, пожалуйста.
Let us thank our speaker again.
Thank you. Thank you.